The Sun is the central star of our solar system and is the most important source of energy for life on Earth. Here's a comprehensive overview of the Sun, covering every aspect. Basic facts: type: G-type main sequence star, G2V. Age: approximately 4.6 billion years. Diameter: about 1.39 million kilometers, 865,370 miles. Mass: 1.989 times 10 to the 30 kilograms, about 333,000 times the mass of Earth. Surface temperature: approximately 5,500 degrees Celsius, 9,932 degrees Fahrenheit. Core temperature: approximately 15 million degrees Celsius, 27 million degrees Fahrenheit. Distance from Earth: about 149.6 million kilometers, 93 million miles, which is 1 astronomical unit, O. Structure of the Sun: the Sun has several distinct layers, each contributing to its dynamics and energy production. Core location: the innermost 20 to 25% of the Sun's radius. Function: this is where nuclear fusion occurs, converting hydrogen into helium, releasing a tremendous amount of energy in the process. The core is where the Sun's power is generated through fusion, powering the entire solar system. Temperature: approximately 15 million degrees Celsius, 27 million degrees Fahrenheit. Radiative zone location: extends from the core to about 70% of the Sun's radius. Function: in this zone, energy generated in the core is transferred outward by radiation, meaning that photons, light particles, are absorbed and re-emitted by atoms, slowly moving toward the outer layers. Temperature: gradually decreases from the core temperature to about 2 million degrees Celsius, 3.6 million degrees Fahrenheit. Convective zone location: the outer 30% of the Sun's radius. Function: in this layer, hot plasma rises toward the surface, cools, and sinks back down in a convective current. This motion causes turbulence and mixing, contributing to sunspots and solar flares. Temperature: between 2 million degrees Celsius and 5,500 degrees Celsius, 3.6 million degrees Fahrenheit to 9,932 degrees Fahrenheit. Photosphere location: the visible surface of the Sun. Function: this is the layer we see when we look at the Sun from Earth. It emits the sunlight that reaches our planet. Sunspots, dark spots caused by magnetic activity, appear on this layer. Temperature: about 5,500 degrees Celsius, 9,932 degrees Fahrenheit. Chromosphere location: above the photosphere, part of the Sun's atmosphere. Function: this layer is visible during a solar eclipse as a reddish glow and is responsible for UV radiation. It plays a key role in solar eruptions and magnetic field changes. Temperature: ranges from about 4,000 degrees Celsius to 25,000 degrees Celsius, 7,232 degrees Fahrenheit to 45,032 degrees Fahrenheit. Corona location: the outermost part of the Sun's atmosphere. Function: the corona is the crown of plasma that extends millions of kilometers into space and is visible during a total solar eclipse. The solar wind, a stream of charged particles, originates in this region. Temperature: surprisingly, the corona is much hotter than the photosphere, reaching temperatures of over 1 million degrees Celsius, 1.8 million degrees Fahrenheit. Composition of the Sun: hydrogen, 74% by mass. Helium, 24% by mass. Other elements: trace amounts of heavier elements like oxygen, carbon, neon, and iron make up the remaining 2%. Energy production: nuclear fusion. The Sun produces energy through the process of nuclear fusion, where hydrogen atoms are fused together to form helium. In the core, intense pressure and heat enable protons, hydrogen nuclei, to overcome their repulsion and combine, releasing enormous amounts of energy in the form of photons. Fusion process: Step 1. 2 protons collide and fuse, forming deuterium, a proton and neutron, and releasing a positron and a neutrino. Step 2. Deuterium collides with another proton to form helium-3. Step 3. 2 helium-3 nuclei collide to form helium-4, releasing 2 protons. This energy takes thousands of years to travel from the Sun's core to its surface, after which it is emitted as light and heat. Solar activity: the Sun is not static. It undergoes cycles and experiences several types of dynamic phenomena. Sunspots: dark, cooler areas on the Sun's photosphere caused by intense magnetic activity. These spots are temporary and can last from a few days to several weeks. Sunspots follow an 11-year cycle, solar cycle, where their number increases and decreases in a predictable pattern. Solar flares, powerful bursts of radiation and energy that erupt from the surface of the sun, caused by sudden releases of magnetic energy. Solar flares can affect satellite communications, GPS systems, and even power grids on Earth. Coronal mass ejections, CMEs, large expulsions of plasma and magnetic field from the sun's corona. CMEs can send solar wind particles toward Earth, potentially causing geomagnetic storms, auroras, and disruptions in communication systems. Solar wind, a continuous flow of charged particles, mainly electrons and protons, ejected from the sun's corona. The solar wind affects the entire solar system, shaping planetary magnetospheres and causing space weather phenomena. The solar cycle, the sun's magnetic field goes through an approximately 11-year cycle known as the solar cycle. This cycle includes periods of increased solar activity, solar maximum, and lower activity, solar minimum. The number of sunspots and the occurrence of solar flares and CMEs are higher during the solar maximum. The sun's role in the solar system, gravitational influence. The sun's immense mass exerts a strong gravitational pull, keeping planets, asteroids, comets, and other celestial bodies in orbit. Energy provider. The sun's light and heat are essential for life on Earth. Photosynthesis in plants depends on sunlight, and the sun drives Earth's climate and weather patterns. Solar wind interaction. The solar wind interacts with Earth's magnetic field, creating phenomena such as auroras, northern and southern lights. Life cycle of the sun. Like all stars, the sun has a life cycle, but it's still in its middle age, main sequence phase. Formation. The sun formed from a collapsing cloud of gas and dust about 4.6 billion years ago. Main sequence. Currently, the sun is in its stable main sequence phase, where it fuses hydrogen into helium. It will remain in this phase for about another 5 billion years. Red giant. After exhausting its hydrogen fuel, the sun will expand into a red giant, consuming the inner planets, including Earth. White dwarf. After shedding its outer layers, the sun will collapse into a white dwarf, a dense, cooling remnant of its former self. Black dwarf. Over trillions of years, the sun will cool further, eventually becoming a cold, dark black dwarf, though no black dwarfs exist yet, as the universe is not old enough. Cultural and historical significance. Throughout human history, the sun has been worshipped and revered in many cultures. Ancient civilizations like the Egyptians, Ra, Greeks, Helios, and Aztecs all had solar deities. Solar eclipses have fascinated and sometimes terrified ancient cultures, often seen as omens. Today, solar energy plays a crucial role in renewable energy solutions. Observing the sun's solar telescopes. Special solar telescopes filter out harmful UV and infrared radiation to safely observe sunspots, flares, and other phenomena. Solar missions. Numerous spacecraft, such as NASA's Parker Solar Probe and the ESA's Solar Orbiter, are studying the sun's activity, structure, and magnetic fields to better understand its influence on the solar system. The sun is vital for sustaining life on Earth, and its influence extends far beyond our planet, affecting the entire solar system. Understanding the sun helps us prepare for space weather events and harness solar energy for future needs.